Hello. In this video, I would like to talk about lesson sequence 1B, question number 4. And what this problem is getting at is that you can use this limit definition of derivative to compute the derivative at a particular point, in this case 3, or you could just, instead of plugging in the value 3, you can use just a general variable x in the limit. And that may be more useful because then your result will be in terms of x, and then you'd be able to substitute any value of x to get the corresponding derivative. So this problem is really just getting at doing it these two different ways, and why perhaps the second one might be more useful because it's more general and you can use it for any value of x that makes sense for that derivative function. Okay, so let's break this up into these three problems. So I'll call this part 1, part 2, and part 3. So the first thing we're going to do is to compute the derivative of x minus x squared at a particular point 3, right? So we're going to compute this limit. Now what I like to do first, so for part 1, what I like to do first is sort of do it in pieces and then put it together. So let's first do g of 3 plus x. Now what does that mean? That means we're substituting this quantity 3 plus h into the function, right? So 3 plus 8, g of 3 plus h, I'm going to, wherever I see an x in the g function, I'm going to substitute in this 3 plus h. So that's going to be 3 plus h, that's the x part, right? Minus the 3 plus h squared, okay? And so what I'll do is just go ahead and simplify this a bunch. So we'll have 3 plus h minus, now don't forget that you're subtracting a whole quantity here, so let's keep it all in parentheses. 3 plus h squared is going to be 9 plus 6h plus h squared. Okay. When you multiply that out using FOIL or distribution, however you like to do it. And now I'm going to do a subtraction here, right? So it's going to be 3 plus h minus 9 minus 6h minus h squared, okay? And now I'll simplify this. It looks like the only terms I can combine would be, the like terms would be the constant terms. 3 minus 9 gives us a negative 6, and h minus 6, so that's a 1h minus 6. So we'll write that. So 3 minus 9, we get negative 6, and 1h minus 6h would be negative 5h. And then we still have this minus h squared at the end of it, okay? So that's g of 3 plus h. That's this part, right? So all we did was this part here. Now let's do g of 3. So g of 3 is going to be just 3 minus 3 squared, right? I'm just plugging in 3 for x, so it's 3 minus x squared, 3 minus 3 squared. So that gives us 3 minus 9, which is this negative 6, okay? So this is my first thing that I did. I'll put a bullet point here. This is the second thing I did. The next thing I want to do is subtract the two, right? I want g of 3 plus h minus g of 3. So g of 3 plus h minus g of 3, right? That's equal to, well, this g of 3 plus h that we have, it's negative 6 minus 5h minus h squared, minus g of 3, which is a negative 6. Right? So remember, when you subtract a negative, that's really adding the opposite, so you're adding 6. So it's going to be negative 6 minus 5h minus h squared plus 6. And now you can see that these two like terms, you can add those, and then you get a 0 because negative 6 and 6 sum to 0. So finally we can say that this is equal to just negative 5h minus h squared, okay? So now we're at a point where I feel comfortable kind of doing the limit, right? So now I want to do this limit, the limit as h goes to 0 of this g of 3 plus h minus g of 3 all over h. And now I'm going to substitute what I just found for this numerator. Remember, I found g of 3 plus h minus g of 3, so I'm just going to put that right into the numerator. And that's going to be negative 5h minus h squared. And that's all over h, right? So notice there's a factor of h in each of the terms in the numerator that we can divide out. So what I'd like to do is I'll rewrite this a little bit, and I'll say this is the limit as h goes to 0. And I'll pull an h out up top, and I'll say that's really h times negative 5 minus h all over h, right? Because if I distribute this h, I'll get negative 5h when I multiply it by negative 5, right? That makes sense. And then h times negative h gives me the negative h squared. And now notice I can divide out the h's, so those cancel out. And I wind up with just the limit as h goes to 0 of negative 5 minus h. And now we know h is going to 0, so now I can sort of directly substitute 0 into h, right? So I know this is just going to be negative 5 minus 0. And I don't need the limit anymore because I'm evaluating at this point. And negative 5 minus 0 is simply negative 5, okay? So this is the derivative, of this g of x equals x minus x squared when x is equal to 3, right? That's what we computed. So essentially we computed this, and if we look at it in derivative notation, we computed g prime of 3, and we said that's equal to negative 5, okay? All right, so let's go on to the next part of this question. So if you don't mind, I'm going to scroll back up, and we're going to look at this part. And now you'll notice the only difference between part 1 and 2, the way I've named them, is that instead of a 3, we just have a general x here. So we're not going to be, we'll have to just drag that x along with us in our calculation. Okay, and what will result here is instead, so this is negative 5, right? What will result here, though, will be something with an x in it. It won't be a number. Okay, so let's do part 2 together. All right, so part 2, we're going to take the limit as h goes to 0, right, of g of x plus h minus g of x all over h, right? And I'm going to do this in pieces as well because it helps me to do things in pieces. It just keeps me organized. So my first piece I'm going to do, I'll put a bullet point there, is g of x plus h. Okay, and that's going to be, again, x plus h instead of a 3 plus h. It's going to be x plus h minus the quantity x plus h squared, right? Notice that it's similar to this 3 plus h minus 3 plus h squared. Instead of a 3, I just have an x plus h. So I can go ahead and simplify that too. So that's going to be x plus h minus, remember it's a quantity, so we'll have to distribute that negative sign. It's going to be x squared plus 2xh plus h squared, okay? And then we'll combine the like terms and we'll distribute this negative. So it's going to be minus x squared minus 2xh minus h squared, like that. And let's see, is there anything I can combine here? Not really. I guess I'll just keep it like that for now. Maybe I'll organize it to put the x terms together. So I'll have x minus x squared again here, right? You'll notice, and then it's going to be h plus h minus 2xh minus h squared, right? And I'll keep those kind of x's that are by themselves over here. Okay, the next thing is just, well, what's g of x? G of x, we don't have to do anything. That's just x minus x squared, right? So we kind of have that done already. And now we want to do the subtraction, right? G of x plus h minus g of x, okay? And what does that look like? Well, that's going to be this whole thing, right, minus the g of x. So it's going to be x minus x squared plus h minus 2xh minus h squared minus this quantity x minus h squared. Pardon me, x minus x squared. Okay, so now you'll notice something when you distribute this negative sign, right? You're going to get a minus x and a plus x squared. So we'll get x minus x squared plus h minus 2xh minus h squared minus x plus x squared, right? And now when we combine, you'll notice you get an x minus an x, so those go away, and you get a negative x squared and a positive x squared, which cancel out because they add to 0. And so we can get rid of those, and we just left with the h minus 2xh minus h squared, right? And now we're going to do the same thing. We're going to put it into the limit formula, right? And we'll say we want the limit as h goes to 0 of this g of x plus h minus g of x, which we already found, this numerator, that's what this is here, all over h. So that's going to be the limit as h goes to 0 of this h minus 2xh minus h squared all over h, right? And again, we'll notice that there's an h, a factor of h in all of the terms in the numerator, so we can factor out an h in the numerator, and we will have this. I'll factor out an h. We'll have 1 minus 2x minus h, right, all over h. Now that makes sense, right, because when I multiply h times 1, I get h. H times negative 2x is negative 2xh, and h times h gives me the h squared. So now I can divide out these h's, and now I won't have that 0 in the denominator when I try to plug in 0. And so we'll have this limit, which will allow us to directly substitute 0 in now for h. So as h goes to 0, we have 1 minus 2x minus h. Hey, that's nice, right? We know h goes to 0, so we don't even need the limit anymore. That's just going to be 1 minus 2x minus 0, which is equal to 1 minus 2x, right? So the derivative, the general derivative, we would say g prime of x, not at a particular point, not at 3 this time, is going to be 1 minus 2x, right? So that's what we're looking for in the second, excuse me for the scrolling here, in the second box here, right? It's going to be 1 minus 2x. Now, what are they getting at in number 3? They're saying, well, look, we calculated g prime of 3 directly with, instead of an x there, we had just had a 3 in there. So we found the derivative at 3, and that was negative 5. We found the general derivative for any value of x, which is 1 minus 2x. Now in part 3, we just want to confirm that our answer for part 2 agrees with our answer for part 1, right? So let me scroll down again, my apologies. So part 3, we have g prime of x again is equal to 1 minus 2x, and now this is a function of x, and so we can certainly substitute in a 3 into here. So if we find g prime of 3, that's going to be 1 minus 2 times 3, which is 1 minus 6, which gives us this negative 5, right, which agrees with our answer from part 1. So it's very powerful to obtain a general form for the derivative, because you're able to substitute any value in for x. So we substituted 3 in, but if we wanted, we could plug in 2 for x here and get the derivative at 2. We could plug in 100 for x and get the derivative at 100. So it's much more useful to have a general formula for the derivative like we obtained in part 2. And that's it. So I hope this helps to understand this problem. Let me know if there's any questions about this. Thank you very much.